You know, when you try to get that perfect, epic landscape shot with your phone, you pan across, hold your breath, and hope for the best. And then, like magic, this flawless, wide image just appears. Well, it's not magic, it's math. And today, we're going to pull back the curtain and look at the seriously cool code that makes it all happen. Let's dive in. So this is the big question, right? Your phone is snapping a whole series of photos that overlap just a little bit. But how in the world does it know exactly where one picture ends and the next one begins so it can stitch them together without you ever seeing the seam? That's the mystery we're going to solve. All right, so the journey to that big, beautiful final image actually starts at the smallest possible level. And I mean small. We're not even thinking about whole pictures yet. We're just talking about individual, single points. Yep. To get from a bunch of separate photos to one seamless picture, you don't start with pixels. You start with math. The entire process is basically just a recipe, a set of mathematical instructions that tells the computer exactly how to move, turn, and blend these images so they fit together perfectly. And this is where it gets really cool. Before a computer can move a whole complicated image around, it has to learn how to do something much, much simpler. Move a single dot from one place to another. This is the absolute basic building block for everything that follows, and the logic is actually pretty straightforward. So this mathematical language really only has two main verbs. The first one is translation, which is just a fancy word for moving something, shifting it from point A to point B. The second is rotation, just turning a point around a center. That's it. Every complex movement we're about to see is just some combination of these two simple actions. And this is how we actually talk to the computer. This grid of numbers, it's called a matrix, is the recipe card. Now, don't worry about understanding every single number. Just focus on what it does. This specific matrix is a command that says, hey computer, take your point, move it 20 units to the right and 5 units up. Simple as that. Now, the recipe for rotation looks a little scarier, I know. It uses trigonometry, sines and cosines, to handle the curves. But the idea is exactly the same. It's just another precise set of instructions. We tell the computer what we want, rotate this point 30 degrees, and this matrix tells it how to do it. Okay, moving one point is one thing. We've got that down. But a photo has millions of points. So how on earth does a computer look at two different pictures and find the exact same points in both of them to link them together? This is where it starts to get really clever. And this right here is the biggest challenge. When a computer first compares two images, it finds thousands of potential matches, but most of them are garbage. They're just visual noise. A little twig on a tree in one photo might look kind of like a crack in a sidewalk in the other. The computer needs a way to separate the good information from all that bad data. The solution is this brilliant algorithm called RANSAC. Think of it like a detective with way too many clues, and most of them are false leads. Instead of checking every single one, the detective grabs a small, random handful of clues and builds a theory. Then it checks how many of the other clues also support that theory. It does this over and over, and whichever theory gets the most votes wins. That's our true pattern, and all the bad data just gets tossed aside. So RANSAC is our critical filter. It finds the real signal in all that noise and makes sure our final alignment is based only on matches we can actually trust. And that RANSAC threshold thing? That's just a knob the developer can turn to decide how strict the filter is. They can crank it up to only accept perfect matches, or dial it back to be a little more forgiving. Okay, so we've used RANSAC to find a solid, reliable set of matching points. We've thrown out all the junk. Now we're finally ready to calculate the master instruction needed to perfectly align one entire image with the other. This is it, the master key. It's called the homography matrix, or just H. It's another 3x3 grid, but this one is the grand finale. It takes all the little movements, the translations, the rotations, even complex changes in perspective, and cooks them all down into a single powerful command for how to warp one image to perfectly match the other. And this single line of code is basically the magic spell. It's telling the computer, hey, take that second image, use the all-powerful homography matrix H we just calculated, and warp it so it fits inside the world of the first image. I mean, just look at what that one command does. It takes this second image, which is flat, and digitally bends, twists, and shifts it until its perspective is perfectly aligned with the first one. It's like they were taken from the exact same viewpoint at the exact same time. And just like that, the hard part is over. So we found our matches, we calculated the master transformation, and we warped the image into place. The two photos are now sitting perfectly on top of each other. All that's left is to blend them together so you can't see the seam. And we do that with a technique called alpha blending. It sounds fancy, but the logic is actually really simple. In the area where the two photos overlap, instead of just picking the pixels from one image or the other, the computer intelligently mixes the colors from both. This creates a gradual, invisible fade from one photo right into the next. Here's the final command that makes it all happen. This function, add weighted, is what does the alpha blending. And you see those 0.5 values? That's the instruction. It's literally telling the computer, take 50% of the pixel color from the first image and add it to 50% of the pixel color from the warped second image. It's just a 50-50 mix. And with that one final instruction, the job is done. The pixels are mixed, the seam completely vanishes, and two separate photos have officially become one continuous, breathtaking panoramic image. The digital stitch is complete. So let's just recap the whole pipeline one last time. Step 1, find matching points. Step 2, filter out the bad ones with RANSAC. Step 3, calculate the master homography matrix. Step 4, warp the image's perspective. And Step 5, blend the images together. 5 clear steps, from separate photos to a perfect panorama. And this is why this is so much bigger than just pretty pictures. These exact same principles, finding features, calculating transformations, warping perspective, this is how self-driving cars see the road. It's how augmented reality overlays digital objects in your living room. It's how movie studios create those seamless, impossible special effects. The digital stitch is one of the foundational technologies of our modern visual world. So the only real question is, what are we going to build with it next?